In today's video, I would like to introduce a very nice problem of Yugoslav Mathematical Olympiad edition 1977. Here is the following information. Let A, B, and C be the natural numbers such that we have this setup: A squared plus B squared equals C squared. We have this equation: A squared plus B squared equals C squared. Okay, our question, we are going to prove that the product ABC is divisible by 60. In the other word, 60 divides this product ABC. In fact, this is very straightforward Pythagorean theorem because it's written on the same form. So in fact, the parity is playing a bigger role in this problem. Okay, this one is strictly related to this product. Okay, if you have this condition verified, and look to the second condition. But if you have one property is not verified, that means you cannot do the other one. So they are joined together. Okay, I would recommend to give the hands to this problem prior to getting into the solution. By the way, don't forget to support us with your like and subscribe. Now let's jump into the solution. We have this equation. We have A squared plus B squared equals C squared. First of all, I'm going to check the parity. Before I proceed with the solution, I'm going to remind you about the Pythagorean theorem. If you have the triangle as a right triangle, we have this side length A, this side length B, this is side length C. We have C squared equals A squared plus B squared. This is very known formula, okay, for the triangle as a right triangle. Based on this information, I'm going to make the connection between this one and our problem. I'm going through the examples. So let's take this one as an example. Let's take 5 squared equals 4 squared plus 3 squared. So for the parity, they have different parity. We have this odd, this one is even, the other one is odd. So it looks like they are not the same in the parity. Okay, let's take another example. Let's take 29 squared, which is 841, equals 20 squared, which is 400, plus 21 quinary square, 21 square. Also, they have different parity. So this one is odd, this one is even, the other one is odd. We have two odds, we have one even. For the first one, we have two odds, we have one even. That means never ever you see these numbers which verify in this equation are even or are odd. All of them are differ in parity. Okay. So based on this information, I'm going to prove one of the case of this one. Let's take if C is a even. If C is a even, implies 2 divides C. 2 divides C implies 4 divides C squared. If 4 divides C squared, implies 4 divides E squared plus B squared, because we have equality. Okay, so this one is telling us 4 divides E squared and 4 divides B squared, because we have the sum here. So this one is telling us 4 divides E squared. That means 2 divides A. That means A is a even. For the B, 4 divides B squared. That means 2 divides B. That means B is a even. In addition, we have C is a even as assumption. In addition, if C is a even, turns down A even and P even. So we have 3 terms are even, which contradict our property. Okay, so in this case, A squared plus B squared differs C squared if they are even. Okay, the case C is a even doesn't work here. Okay, that means ABC not divisible by 60 if we have this property is not verifying our condition, because this one and this one are related. Okay, so now let's move on to the next case when we have C is an odd number. So let's check the case when we have C is an odd. C is an odd. If C is an odd, that means one of these numbers, A or B, is odd. That means the other one is even. So without loss of generality, assume A is an odd. If A is an odd, that means B is an even. Since C is an odd, let's set let's set c equals 2m plus number 1. Okay, I'm going through the cases. Let's take the smallest value of a equals 1 as an odd number to see what's given us if a equals 1, because the solution of this equation is related to this property ABC divisible by 60. Okay, I'm going to replace a with its value into the original equation to see what's given us. We'll have 1 plus b squared equals c squared. So we'll get b squared equals c squared minus 1. This one is written on the form of the difference of two squares. I'm going to factor out this one. It's giving me c minus 1 factor c plus 1. I'm going to replace c with its value with this setup. So I will get b squared as an even number, this is even, equals c, which is 2m plus number 1 minus 1 factor. C will be replaced with 2m plus 1 plus number 1. I'm going to simplify this one more. I will have here number 1 will be cancelled out, 1 minus 1. I will be left with 2m factor 2m plus 2, 2m plus 2. Then I'm going to take number 2 outside of this one as a multiplier. Is multiplied by these 2 is giving us 4. Is multiplied by m is multiplied by m plus 1. I'm going to distribute this one. I will have b squared equals 4m squared plus number 4m. If you take a look carefully, this term 4m squared plus 4m, which equals b squared as a perfect square, because we're assuming this one is a perfect square, is strictly inferior than 2m plus 1 quaternary square, is a superior than 2m quaternary square. This is integer number, this is integer number. So since this term is located into two consecutive squares, is between two consecutive squares, this is impossible, contradiction. This means a equals to 3. Since a not equal to 1, that means a equal to 3. It could be the next possibility. Okay, I'm going to take this value and insert it again into the original equation to see what's given us. We'll have 3 squared plus b squared equals c squared. By taking 3 squared to the right hand side of this equation, we'll get b squared equals c squared minus 3 squared. This is also a difference of two squares. I'm going to factor out this one on the form of the product. You will have c minus 3 factor c plus 3. I'm going to do the same thing. I'm going to replace c with this setup. So we'll get 2m plus 1 minus 3, because c is an odd number, is multiplied by 2m plus number 1 plus number 3. So I'm going to simplify this one. This one is giving us 2m minus 2. This one is giving us 2m plus 4. I will have b squared equals, from here I'm going to take number 2 as a common multiplier. From here also I'm going to take number 2 as a common multiplier. I will have 4, I will have 2 is multiplied by 2, which is 4. So I will have 4 factor m minus 1 factor m plus 2. So I don't have to distribute this one out. I'm going to apply the square root on both sides. I will have b as an even integer equals to square root of m minus 1 factor m plus 2. So I have ended with this expression. If you take a look at this expression, the left hand side of this equation is an integer, okay, as an even number, but the right hand side of this equation is not integer. In order to maintain this equation and make this equality works correctly, we are going to create a perfect square here. We have to have the condition a perfect square in order to have this one as an integer. Okay, So this term inside of the square root must be a perfect square. I'm going to distribute this one. So this term, m minus 1 factor m plus 2. By distributing out this one, I will get m squared. So I will have 2m minus m, which is plus m, minus the last term, which is plus the last term, which is minus 2. So this one, it will be written, this term, m squared plus m minus 2 is strictly inferior than m plus 1 quantity squared is strictly inferior than m plus 1 quantity squared and strictly superior than m squared. Okay, let's take an example. When m starts with number 2, if m starts with number 2, we'll get 4 here. I will get 4 plus 2, which is 6, 6 minus 2, which is 4. Impossible to have 4 is strictly inferior than 4. That's when we have to increase m up. We are going to stay with the same example. Let's move on to check with this one. M equals 2. That's mean we have 2 plus 1, which is 3, which is 9. This one is verifying m equals 2, but is not verifying this one. So let's increase m with one more number up. So I'm going to take m equals 3. M equals 3, that means this is 9. This becomes 9. 9 plus 3, which is 12, minus 2, which is 10. That means 9 is strictly inferior than 10, which is correct. Okay. This one is also correct. Whatever you replace above these points, we will have always this properly verified our condition. Okay. So that means since this one is located between two consecutive terms, as I did in previous proof, that one is impossible. That means this one is not a perfect square above these points. For all m is strictly superior than 2. When we have m strictly superior than 2, since it's not perfect square above these points, that means is a perfect square below this point. That means this one is telling us m is inferior or equal to 2. Previously we were working on the setup and came up with this result. So we found m is inferior or equal to 2 because this term is not perfect square due to the m strictly superior than 2. We found this product, which is this one, is a perfect square if only if we have m inferior or equal to 2. Okay, so this one is telling us m is taking two values, is taking number 1 and number 2, but m equals 1 doesn't work here, because so if m equals 1 implies b equals 0, because when so that means b equals 0 is not verifying this condition, because if you replace b with 0, we'll get a square, which is 9. 9 equals c square, which that means a equals c, which is impossible, because since we have the sum of two squares equals c square, that means c is strictly superior than a and c is strictly superior than b. C is strictly superior than b and c strictly superior than a. In addition, b must be a positive integer, because we have the natural numbers. Natural numbers doesn't count 0. Okay, so that's mean this case doesn't work. That's mean m equals 2. If m equals 2, that's mean b. If you're going to replace m with number 2, we'll get here 2 minus 1, which is 1. M equals 2. 2 plus 2, which is 4. 4 is multiplied by 1 is giving us 4. Square root of 4 is giving us 2. 2 is multiplied by 2 is giving us 4. That's mean b equals 4. B equals 4, and we already have a equals 3 by assumption. Then now we are going to calculate c by replacing a and b into the original equation. So I will have a squared, I will have 3 squared, which is a squared, plus b squared, which is 4 squared. This one is giving us 25, which is 5 squared, which equals c squared, which is verifying our condition. This is replaced with a, this is replaced with b, this is replaced with c. So this statement is verifying our condition. So that means c is bigger than b is bigger than a, and also if you take the product, a is multiplied by b is multiplied by c equals 60. A is multiplied by B is multiplied by C is giving us 3 is multiplied by 4 is multiplied by 5, which equals 60. So according to the divisibility statement, 60 divides this product ABC. In the other word, ABC is divisible by 60. That means we'll have ABC, according to the divisibility statement, ABC equals K is multiplied by 60. We know 60 equals 3 is multiplied by 4 is multiplied by 5. Okay? So we'll have K is multiplied by 3 is multiplied by 4 is multiplied by 5. So this case, what I have shown, this is just base case, because ABC must be bigger than 60. So we are going to look for another triplet where we have another condition verify our setup. Let's take another triplet as an example. If we are going to take 20 square plus 21 square equals 29 square. 29 square is the same as 841. So always we have 29 as a C is bigger than A is bigger than B, as we have here. The second thing, I'm going to take the product of these terms. Let's call this one as a B, as an even number, and this one equals A as an odd number. This one equals C as an odd number. So now I'm going to take this product of these numbers. A is multiplied by B is multiplied by C, which equals 20 is multiplied by 21 is multiplied by 29. I'm going to extract these numbers 3, 4 and 5 from here. So 21 is the same as 3 is multiplied by 7. 20 is the same as 4 is multiplied by 5. So I'm going to put 3 in the front, 3, and extract number 4 and number 5 from 20, because 20 equals 4 is multiplied by 5. And then is multiplied by 7 is multiplied by 29. If you calculate this term, 203, which equals K. Okay? So this term equals 60. That means ABC equals K is multiplied by 60. Where is K is a some natural number, which K equals 203. Our case, when we have K, it was 1. K equals 1. Because 60 equals 60. Okay? That means 60 divides ABC. Unique triplet, you will have another K with the same divisor. Now the most important thing that I'm going to extract from here, the divisor of 60. Okay? Now every single triplet which verify this condition, it has this term 3, 4, 5, which is 60. So we are going to look for another triplet. We will have another K which is bigger than this one, then verify this condition. In general, so generally I will have ABC equals K is multiplied by 60, which K is multiplied by 3 is multiplied by 4 is multiplied by 5. What is a K is a some natural numbers, but K must be positive. K equals 0 doesn't work. That's what we have proven before. Okay, this one is telling us therefore 60 divides this product ABC. In the other word, ABC is divisible by 60. Okay, so I have proven this one. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.